Today in this video, we're going to be talking about different kinds of statistical graphs, graphs that are used to present in different ways. And then we're also going to take a look at the next section, which is critical thinking with graphs. Just looking at some, what would make a bad graph. So first, what are all the different kinds, and then what would be a bad graph? To start off with, we'll start off with the bar chart. Bar chart is different than a histogram. Bar charts typically give you a category. Categories that's going to be a qualitative type of graph. Like this would be, how many people prefer bananas over grapes. Then we have what's called a frequency polygon. So we did a frequency distribution, and so this would then just be, it's a line graph connected. You could probably just get away with just the dots as well. Whether you've got them connected or not isn't necessarily important, but usually it is a line segment connecting to the points that are located directly above the midpoint values of them. This is quantitative, and so we would have then values in there. These can have multiple sets of data, so that's kind of a nice thing. We can compare different things by doing multiple frequency polygons. They get their name polygon because, technically when you connect segments, you're giving yourself a polygon. Think about your geometry days. The next one here is what's called an ogive. An ogive uses cumulative frequencies. So this could be technically, I suppose, cumulative as far as it could be your percents cumulative, but typically what is done is just adding up the frequencies themselves. You're typically just doing cumulative frequencies, not cumulative relative frequencies or cumulative percent frequencies, even though I suppose you probably could. It uses class boundaries along the horizontal axis and cumulative along the vertical axis. Then we have dot plot. The advantage to this is they're really, really easy to make. You're literally just counting. It could be quantitative, but most likely it's qualitative. But this one, it could go either way. Like here's an example of quantitative. How many people have 2 brothers and sisters? How many people have 3 brothers and sisters? So on and so forth. They're just easy to make. They're flexible. It's probably an underutilized style of making a graph because it is so easy to make them. Then we have what's called a Pareto chart. Pareto charts, those are used for qualitative. So again, we're talking about labels here. Labels for different countries, or labels for different, in this case, things going on with work where you have unsatisfactory customer service. What are the things that they're not satisfied with? This is a bar chart, even though I have seen them. I got this one here. It's kind of a combination of the two, sort of. It's reversed. But they are typically a bar chart. That gives added attention to more categories. Notice it's the most, then the next, then the next, then the next, then the next. This is the most, then the next. So it orders them in order of their percentage or their frequencies. Whichever, so most going to least, or you could order at least going to most. That doesn't really matter. But if that's what you're doing, if you're ordering from most to least or least to most, then you're talking about a Pareto chart. This little deal down here, this is my comment. Sometimes you may see an additional line representing a cumulative percentage of frequencies. It's not necessarily part of the Pareto chart. Sometimes they put them in there, like this one, but the actual Pareto are the little bars down here going from most to least. Again, it's qualitative. You got labels typically along the bottom where you're going to have your frequencies or relative frequencies, percent frequencies. And when I just use the term relative, that almost implies percent. I know they're technically not the same thing, but we calculate our relative frequencies typically for the purpose of switching them over to percent frequencies. So we've got our frequencies or relative frequencies are going to be, of course, on there as well. Stem and leaf, you probably saw these back in like an Algebra 1 class. They're really weird to look at, and they're very confusing if you don't know how to use them. The important part is what's called the key. somewhere on there, there's got to be something that tells you how to read the thing. And here's the key for this one. It says 2 and then a bar and then a 5 means 25. So maybe it means 250, maybe it means 2,500. It has to tell you, somehow tell you what it means. So like here we're counting with by 0 here, so this would literally just be 6, 7, 8 of them, but this would be 10, 12, 13, 14, 17, 17, 17, 18, 19. So I'm just putting, the key tells me to put this number in front of whatever number I'm looking at. So like here, this is 31. This 3 with the 6, of course, is 36. So here's my 10s, my 20s, my 30s, my 40s, my 50s, and so on and so forth. But you got to have a key, because it could be going by tens, it could be going by hundreds, could be going by thousands. I suppose people could get really creative and write all kinds of crazy things. But those are called a stem and leaf plot, or a stem plot. Here we're usually talking about quantitative data. Quantitative data when we look at these to create. This type of graph, like a histogram, makes it easy and quick to recognize which category is the highest or lowest just by its shape. If you were collecting data right away here, I would know, hey, in the tens, there's more of them than anywhere else, which is really nice to be able to quickly analyze that and know. Or in this one, I've only got 1 in the 50s, and it's literally at 50. So you would know that that's getting smaller as you go here. So visually, even though it is numbers, visually you're getting an idea of what's going on without necessarily having to go through the process of creating an entire histogram. Again, take this one. The key here is 2, 1 is 21, so it's the same key basically as that one up there. If you're not given a key, so like over here, does this mean 40 or 49, or does it mean 400 and 490 or something like that? Don't know. You don't know unless you have the key. So if you make a stem and leaf, you've got to give a key someplace. It doesn't have necessarily a spot, but someplace around here, you've got to have a key. Pie charts. Pie charts are used usually for qualitative data. Qualities like, hey, what's your favorite kind of pie? Is it apple pie? Is it coconut cream pie? And again, this is generally going to be percentages when you go around. I don't think I've ever seen one that wasn't percentages. Percentages as you go around. Comment in your assignment if they ask you to make a pie chart. Skip the making it. I know you do that stuff back in like the 9th grade, maybe even 8th grade. I'm not going to have you sit there with a protractor creating a pie chart. Quite frankly, we just don't use these a lot. Scatter plots. Okay, now scatter plots we're going to use more. Towards the end of the class, when we talk about regression, we have to talk about things like the line of best fit type of things. Now, you've seen scatter plots. You've probably made scatter plots in your graphing calculator. This one is one that we would use quite often. It's for quantitative data, where we have an independent variable, that's always the x-axis, and then we've got a dependent variable, that's the y-axis. And it's especially helpful, like I mentioned, in regression, when we're looking to find a pattern within the data. It doesn't have to be exact, it's just a general trend. In fact, back in about the 7th grade, you probably called it a trend line, and then later on learned to call it a line of best fit. So it's just trying to see if things go together. Scatter plots. Time series. The name sort of tells you what's going on here. You are looking at times of day. Could be times of the year, could be, whatever time unit you want to talk about, and when things are high or low. So maybe like in a resort setting, and you want to look at when you're the busiest. Most people would assume would be during the summer, but maybe you would take the average amount each month, or the average amount maybe each week, and plot it out for the year. And then you could see, yeah, this is truly when we're the busiest. But it could be by the minute, could be by the second, I suppose, if you're maybe doing some close calculations with science or something. And then it could be that it's, like in this case, by the minute. quantitative information. And this comes out of a textbook. That's why it says second edition by Edward Tuffy. So this is actually a book. In his book, he makes a few points. For small data sets, fewer or less, you could just simply use a table instead of a graph. People can absorb to a point just the numbers, just the values of the data. But you get more than that, and it gets really tough for people to see any kind of patterns at all. But if you have fewer than 20 is his rule. I personally think it would be more like 10, but he's of the opinion fewer than 20. A graph of the data should make the viewers focus on the true nature of the data. In just a couple of minutes, we're going to look at bad graphs, things that don't have you focus on the true nature of the data. So what is the truth about what we're trying to present? Don't distort the data. Construct a graph to reveal that, again, there's that term, true nature of the data. I like this comment he makes. Almost all the ink in the graph should be used for data, not for other design elements. That'll make more sense as I go through what makes a bad graph, what I mean by that part there. Some people will think of it as an art project when they're creating graphs, and they're distracting you from the data. So let's go into that. Let's talk about bad graphs. What makes something a bad graph? And it really has to do with the points we just pointed out. The intent of a graph is to draw your eye to the true nature. Taking, for example, this one right here. Right there, I look, hey, U.S. Airways, they're on time the most. Unless you take time to read numbers and notice, hey, these two have the same numbers. But they drew this one longer and made it red so it attracts your eye more. So that's not representative of the true nature of the graph. That's a misleading statistic in the form of a bad graph. And we've talked about misleading statistics already. This is a form of misleading statistics, in the case of what's called, again, a bad graph. Look at this here. They've even got this one shorter than that one, even though this one's on time more than that one. So again, statistically misleading, and they're doing it with the tool of a bad graph. I would say this one was by design. I don't know how it couldn't be by design. Sometimes bad graphs are, I would say, they're not doing it on purpose. But then there's other times like this is, oh yeah, they're definitely doing this on purpose. All right, so I'm going to give you some categories here. Pictographs. Pictographs are misleading. They can be misleading. Sometimes these things are drawn in 2D, sometimes drawn in 3D. What makes them misleading is the pictures themselves can add more weight to a different part of the graph. What I mean by that is, literally, if you take a look at these, do you notice that the oranges are a little bit bigger circles than the apples? So you already sort of have a element here of a visual discrepancy just based off of looking at the size. Now, yes, the numbers do go bigger. So I would say whatever they're trying to show here, world production of fruit, yeah, more oranges are produced than apples. But you've got a visual thing here, not just a numeric thing, that's emphasizing it, and that creates a bad graph. So pictographs, what it means is I'm using pictures instead of, most of the time with a polygons, you might have X's or you might have dots. But as soon as people start putting pictures in there, you probably need to be leery of what they're doing. And again, it's not necessarily malicious on purpose, misleading on purpose. Sometimes people are just trying to make a really nice looking graph to present to people, and they gotta, spice it up a little bit. But it can be a misleading technique. This one here, same kind of thing. It's a pictograph, but the sheer size of this candy corn implies much, much larger, because it's not just height, which we're looking at the frequencies over here. The height is what actually matters. But when they do these two-dimensional things, you have height and you have width, which again visually literally adds more weight visually to what you're looking at. So like this looks to be about maybe 18, and this is about 36, so about twice as much. Michael collected about twice as much as Cheyenne. Excuse me, Shayna. Twice as much as Shayna. But when you're looking at it, oh my word, it just feels like 3 times or 4 times as much just because of the way the graph is. Here's another example of just a two-dimensional pictograph, same issue. The garbage can is getting bigger, make it feel weightier over here instead of just simply looking at the heights. So it's not giving us the true nature. This one, this is and I apologize, these are old pictures obviously that I pulled together years ago of bad and misleading statistics using bad graphs. This one's a little trickier to catch, but this is a misleading bad graph thing, again, not necessarily maliciously, but it shows up a lot, and that's right here. This is what's referred to as a non-zero axis. Okay, so it makes it just completely feel like, oh, these are so much more than each other. When the truth is, if it went all the way down to zero, the heights here, yes, they would be going up, but they wouldn't be going up by as much as they feel like they're going up. This one just makes it sound like, this guy's coffee shop is way better than anybody else's. When the truth is, yep, it is better, but not. It looks barely a difference here at all. 2 cups of coffee better? Not much different. So a non-zero scale. Non-zero scales, when I see misleading statistical graphs as far as bad graphs, that's usually the one that I see. Here's another example of that. Same thing, a non-zero graph. Look at the difference here. I mean, it's just really 2 miles an hour. But looking at the graph, it feels like it's twice as fast between this year and this year. So very misleading graphically because it's twice as tall. So a non-zero graph. This one here, does this prove global warming? You look at it, the temperatures are going up and up and up. It seems like global warming's a thing. And I'm not saying global warming's not a thing. I'm saying, I'm sure I'm being cynical. I'm not saying it's not a thing, but this is a bad graph. Because if you're going to show monthly temperatures on average, you should show the entire year, not just 6 months. This gives a bad trend line because we all know that after July, it might go up a little more in August, but then come September, it's going to start doing this. So giving a full picture, if you're giving something that goes in a cycle, show the entire cycle. Don't just show a piece of the cycle. Otherwise, it's very misleading. I'm sure you've picked this out by now. But again, we've got another non-zero. So that's an example in this one. And I would argue that the change of color has something to do. If people play with colors, you got to be careful. People know that certain colors, reds, tend to catch your eye more. So that's going to be something that's going on there as well. Here's another one, rainfall. Again, where's the rest of the year? Literally, they're showing 3 months of rainfall here. Is there something really whack going on in February? Or is this just because we're only seeing a very small piece of the big picture? If you're making a graph that involves a cycle, show the entire cycle. Show it more than once. And yes, this one also has a non-zero scale. So this one's got a couple of different problems. We got 0 scales here. No issues there. Got anything that you can pick out on this one that's misleading? I don't know if you noticed or not, but they are 0 scales, but the scale that they're going by is not the same. It's actually the exact same pieces of data. It's just what the scales are set to. Now, I would actually argue that this gives you a closer look at whatever it is you're analyzing. Uh, I don't like when there's lots of stuff above. I'm just showing you it can be misleading. This one is misleading in the sense that it doesn't feel like it's changing much. I would argue that when you're going to put together a graph, your graph from the bottom to the top should encompass most of the data. So here there's just a lot of empty space. And so it's a little bit misleading, like there really wasn't much of a change there. I mean, I could make anything look flat if I zoom out far enough. This one, I don't even know what to say. I mean, it's just horrible. I don't even know what you could, other than talking about the UK. Yeah, okay, they're 50%. I don't even really, my mind can't truly compare this stuff very well. I mean, you can't even really read this. They even stopped giving percentages because the parts are getting so small. And so that's just a bad graph all the way around. All right, so from these two sections, I want to explain what I want you to be able to do, because I know I went kind of fast. I want you to be able to just match, this is open note stuff, just match the titles of graphs to the kind of graph. And then if I give you a bad graph, tell me what's bad about it. That's what I expect you to be able to do from this particular two sections that I covered today. That's it. You have a good day.